Welcome to today's session. I hope I am audible and the slides will be visible too. We will start the lecture in a couple of minutes, let's say 2 minutes. Let's begin today's class. Uh, in the previous class, so we had covered this first order system, second order system, and when we discussed about this higher order systems, later on we looked upon this block diagram representation and we studied it by an example of this level control example and represented it using open loop system as well as closed loop system. So we studied how to represent any kind of closed loop by using these blocks and inputs and outputs, the corresponding to each of this controller, final control element, process, measuring device. We generated this feedback control system. So in today's class, we will be first covering few of these numericals, three numericals related to this closed loop system. So how to calculate the closed loop transfer function that we will see, then take, let's say, three examples of that. After we are done with this, we will study this feed forward control and feedback control in detail and look into this servo and regulatory control problems for this closed loop system, and later on we will again solve the numericals for those. So this is our plan for today's lecture. So the first question for today that we are looking is from GATE 2012, question number 42, and the question is, the block diagram of a system with proportional controller is shown below. So we have this block diagram. We will see, you can call it as output, or you can call it as input or the set point. You can be also called as another input. In general, you can be called as an input, or we can call it as set point. Then KC is a controller, proportional controller. So we haven't studied this controller yet in detail yet, but we will just take a look into this example. Then we have this transfer function, to transfer function. And we have been given a unit step input is introduced in the set point. So we are introducing a step change over here. The value of Kc, which provides a critically damped response for u equal to 0, tau p equal to 8, and tau m equal to 1 is dash. So basically, we have been asked to find the value of Kc if this entire system, if this entire closed loop system behaves as a critically damped system. Basically, the response, if it is critically damped, then we have to find this value of Kc, that is the controller gain, you can say. So let's look at the video solution of this, and then we can discuss the solution in detail. This is question number 42 of GATE 2012. I will just share the video. Just wait a minute. Let me know if the video voice is not audible.
Hello everyone, we are solving question 42 of GATE 2012 chemical engineering paper.
I'll just keep reading the question.
Input value system for solution. So in this given question we have been given the value of tau m as 1, the value of tau p as 8 and the value of u as 0, and we have to find the controller gain for the proportional controller Kc for critically damped system. And we know that for critically damped system the value of zeta is equal to 1. So what we will do is we will find the transfer function of this entire system and then find the value of zeta, equate it to 1 to find the corresponding controller gain. So let's write the transfer function of the system. So since the value of u is 0, we can write g of s as c upon rs, or the transfer function of this entire block diagram can be written as the numerator will be the multiplication of these two blocks, that is Kc into 1 upon tau ps plus 1. The numerator will be multiplication of all these three blocks 1, 2 and 3. So 1 plus multiplication of all these three blocks, so it will become 1 plus Kc 1 upon tau ps plus 1 and 1 upon tau ms plus 1. We can replace the value of this time constants for this measurement block and process block in this equation and simplify it. So it will become Kc 1 upon 8s plus 1 upon 1 plus Kc 1 upon 8s plus 1 upon tau m is 1, so it will become s plus 1. Let's just simplify this. So we will multiply these two terms, and this 8s plus 1 and s plus 1 will come over here. 8s plus 1 s plus 1 plus Kc upon 8s plus 1 into s plus 1. This we can cancel out and we can write the transfer function as g of s is equal to Kc s plus 1 upon we have 8s plus 1 s plus 1 plus Kc. Now we can open this bracket and simplify this further to write this as 8s square plus s plus 8s plus 1 plus Kc. So this will become minus plus 1 plus Kc. Now from over here we can see that this is a second order system, and in general a transfer function of the second order system we can write it as Kp upon tau square s square plus 2 zeta tau s plus 1. So we need to change this equation in this form. So that is the last term of the numerator should be 1. So we will divide this equation by 1 plus Kc and again simplify it. It will become Kc s plus 1 upon 1 plus Kc upon 8 plus 8 upon 1 plus Kc s square 9 into 1 plus kc plus 1. Over here it will become s. So now we will equate both of this equation, and we can compare the coefficients of the numerator to find the desired value of tau square and 2 zeta tau, and then we will be having tau square is equal to, from over here it is 8 upon 1 plus kc, and 2 zeta tau we have 9 into 1 plus kc. Now the value of zeta we have been provided as 1, since this is a critically damped system. So from here we will be having tau is equal to 9 upon 2 1 plus kc, and tau square we are having 8 into 1 plus kc. So let's just equate both of this. So we will be having 9 upon 2 into 1 plus kc whole square, that will be equal to this term 8 into 1 plus kc, 8 upon 1 plus kc. So this term will become 81 upon 4 1 plus kc whole square plus 8 upon 1 plus kc. This will get cancelled out, and we will be having 1 plus kc is equal to 81 upon 8 into 4 will be 32. So from over here we can find the value of kc as 81 upon 32 minus 1, and this will come around 1.531. So for if the system is critically damped, we kept the value of zeta as 1 and found out the kc, that is the controller gain for proportional controller, or the proportional constant for this controller gain, as 1.531. So the final answer we will select as option C.
Was that question clear, or do you have any doubts regarding this question? So in this, we simplified this block diagram to find the closed loop transfer function relating the output C and the input of the set point R, C by R. So we usually write this transfer function, the numerator will be multiplication of these two blocks, plus the denominator will be the multiplication in the feedback loop. So basically this is our feedback loop. So all these three blocks will get multiplied in the denominator plus 1. And then for critically damped system, we put this zeta equal to 1. So that property we used, and find the controller gain for proportional controller. If you have any doubt, you can write it in chat box. So the next question is on a similar basis. It is question number 61 from 2015, and the question is: the block diagram for a process with feedback control for output deviation variable h is shown in the figure below. All transfer functions are given with a prefactor s in minutes. A unit step change is made in the set point at t equal to 0. The time required for h to reach 50% of its ultimate value in minutes is dash. So here again we are giving a step change in the input, that is changing the set point by step change, and correspondingly we have to find the time that will be taken by the system to reach the 50% of the ultimate value of this. So what we will do is we will first find the transfer function relating this output h bar s upon set point, and then on the basis of that we can find the ultimate or the final value of the output, that is h of infinity, and then we can calculate the time taken by the system to reach this 50% of h infinity. So let's take a look at the video solution.
multiplication variable h, percent of the ultimate value is h. To find it, let's start solving the question. So we can write the relation, the transfer function between h of s and the input set point hsp of s as the numerator of this transfer function will be the multiplication of these three blocks. Since we are calculating the correlation between this and this term, it will become gc gf gp upon 1 plus, in the denominator we will be multiplying all of these three blocks plus 1. So it will become gc gf gp and the gm. So all this term will be in s domain. So let us write the individual transfer function of each of this block and simplify the equation. So gc we have been given as 0.5s, g of f we can write it as 0.2 1.5s plus 1 into 1 upon 0.5s upon, we can write this as 1 plus 0.5s 1.5s plus 1 into 1 upon 0.5s into 1. So you can cancel this term and then we can simplify this as 0.2 upon 1.5s plus 1 upon 1 plus 0.2 into 1.5s plus 1. So this will become 1.5s plus 1 plus 0.2, and the numerator of both this term will get, the denominator of both this term will get cancelled out. So you can write the final equation as 0.2 upon 1.5s plus 1.2. This you can also write it as 2 upon let's just take 1.2 common from this. So that is, we will be having h bar s upon h sps is equal to 0.2 upon, let's take 1.5 common from this. It will become 1.5 s plus 1.2 upon 1.5. This will become 2 by 15 upon s plus 0.8. That is, we are having h bar s upon hsp. So in the given question we have been given a unit step change in the set point is made. So since we are providing a unit step change in the set point, that is hsp will become 1 upon s. So let's just replace it over here. 1 upon s is equal to, transfer function we found out as 2 upon 15 upon s plus 0.8. Over here it is bracket, that is the output will be 2 upon 15 into 1 upon s into s plus 0.8. Now to convert this into time domain, we need to take this inverse Laplace of this term, L inverse of h bar of s. So for that we need to simplify this equation into this partial fraction. So that is, we can write this as 2 by 15 into a upon s plus b upon s plus 0.8. So now using this equation we have to find the value of a and b. So what we will do is, we will first multiply this equation by s, and then we will be getting the value of either a or b. Then again we will be multiplying the equation by s plus 0.8, that is basically this term, and put the value of s is equal to minus of 0.8, and then again we will be getting the other coefficient. So that is basically we are solving this partial fraction to find the constants a and b, and we will be having, you can do this calculation, and we will be having a as 1 upon 0.8 and b as minus 1 upon 0.8. So we can put this value of a and b in this equation, and we will be having h bar s is equal to 2 upon 15. A was 1 upon 0.8, so 1 upon 0.8 as b was minus of 1 upon 0.8, so it will become minus of 1 upon 0.8, and we had s into s plus 0.8. Now we have to take the Laplace inverse of this term, so it will become h of t will be 2 by 15. So let's just simplify this further by taking this 0.8 common, so it will become 2 into 15 into 0.8, 1 by s minus of 1 upon s plus 0.8, and this will become 1 by 6, 1 upon s we are taking Laplace inverse of this entire term. Now it will become 1 by 6. Laplace inverse of 1 upon s will be straight away 1, and 1 upon s plus a is e raised to minus of 80, so it will become e raised to minus of 0.8t. So over here we are having our output equation, and to find the final value we can simply put t tends to infinity, and we will be having the value of h at steady state, or the ultimate value, as 1 upon 6 into 1 minus e raised to minus of infinity. So this will become 0. That is the ultimate value. H upon infinity is 1 by 6. Now in the given question we have to find time at which h is half or 50% of the ultimate value. So it will become half of 1 by 6, that is 1 upon 12. So you have to find the time at which the value of height, or h, is 1 by 12. So in this equation we can simply put h is equal to 1 by 12 and equate it to find the value of time, that is 1 minus of e raised to minus of 0.8 t. So this will become 1 by 2 is equal to 1 minus of e raised to 0.8 t, that is e raised to minus of 0.8 t to 1 by 2. So you can take log on both the sides, and it will become minus of 0.8 into 2 is equal to minus of 0.693, that is t is equal to 0.867. So the time taken by the system to reach 50% of the ultimate value, that is 1 by 12, will be 0.867 units. So we will write the final answer as 0.867.
Let's look at next question. So the next question is similar to the previous one. So the question is, consider the following closed loop system with GP, GCS transfer function of process and controller respectively. For a unit step change, YSP, the change in the value of response Y at steady state is dash. So just similar to previous question, we will first find the closed loop transfer function. So that will be Y upon YSP is equal to GCGP upon 1 plus GC GP, and then we have been given a step change in the input, that is YSP is 1 by S. From that we can calculate this YS 1 by S GCGP upon 1 plus GCGP, and then we have been asked to find the change in the value of response at steady state. That is basically we have been asked to find the YSP at the final value, that is Y infinity we have to find. Let's quickly take a look at the video solution.
Of yes, value of log and the value of, write the transfer function y upon ysp s. So the numerator will be multiplication of gc and gp upon 1 plus this term gc into gp. So from this we can get the value of y, and in this question we have been given YSP as unit step change, and we can replace it to find the value of the output, and then we can find its ultimate value. So let's just simplify this numerator GC upon GP. So it will become GC upon GP is equal to 0.2 1 plus 1 upon 0.5 s. GP will be 10 upon s plus 1 2s plus 1. So we can also write this as 0.2 into 10 will be 2. 0.5 we can bring it 1 upon 0.5 we can write it as 2, so it will become 1 plus 2 upon s 1 upon s plus 1 2s plus 1. So this two we can further simplify it as and ultimately we can write that GC GP is equal to 2s plus 2 upon s into s plus 1 into 2s plus 1. Now the transfer function of this entire block and of the entire system will be y upon ysp is equal to GCGP upon 1 plus GCGP, that is G star. Now we can further simplify this as 2s plus 2 upon this entire term, and if we simplify the denominator, so this will get cancelled out and we will be having s plus 1 2s plus 1 plus 2 s plus 2. So this is we are having the transfer function. Since we have to find the ultimate value of the system, we don't need to simplify or open this bracket any further. Now YSP we have been given as step input, so we can replace it as 1 upon s, and again simplifying this further we can write the value of YSP is 1 upon s into 2s plus 2 s plus 1 to s plus 1 plus 2s plus 2. Now the ultimate value of the system, we can find it as ultimate value of the steady state value as limit s tends to 0 as ys. So let's just replace this ys over here, and we will be having s into 1 upon s to s plus 2 upon s plus 1 to s plus 1 plus 2 into s plus 2, where over here we have to put s is equal to s tends to 0, so we have to put s equal to 0, so it will become s will get cancelled out to 0 plus 2 upon 0 and anything will be 0 plus 2 into 0 plus 2, that is yss is 4 by 4 is equal to 1. So the ultimate value of the system will be 1 since we are providing the step input of unit magnitude. So the final answer, we can report that for a unit step change in the set point YSP, the change in the value of response at steady state, that is ultimate value, will be 1.
Now let's take a look into the further theory of this feedback control and feed forward control. So we had discussed this feedback control in brief. So today we will be discussing it in detail. So a feedback controller responds only after it detects the deviation in the value of controlled output from its desired set point. So in our earlier lecture, we had studied that, let's say if I am having a process GP, this is my input YSP and output Y. So in order to control this, I can take the output reading, pass it through some measurement, and then feed it again back. And over here, we will be having our controller block. So since we are feeding this output back towards the input, we call this as feedback control. So you can see that we need to measure the output in this case. So that is what it says, that it responds only after it detects a deviation in the value of controlled output. So on the other hand, feed forward controller detects the disturbance directly and takes an appropriate control action in order to eliminate its effect on the process output. So let's just consider this case of a simple distillation column. So here we are providing feed, distillate, and bottom, and our goal of this control system would be to, let's say, control the quality of this distillate. So what all disturbance can be in the system? So the first disturbance would be in the feed. So if the feed composition changes, then my distillate composition would also change. So if we have to employ this feedback controller, what I will do is I will measure the composition of the distillate over here. So here we will be measuring the distillate composition and using the feedback loop over here and control the output valve on the top of this distillation column. So let's say if my distillate composition increases, then correspondingly this valve will take manipulative action. However, we won't be changing this input F. So that is our feedback controller. Similarly, in case of feed forward controller, what I will do is if my distillate composition changes, then I will change the valve by by estimating how much my distillate composition will change by using this feed. So what we will be doing is we will be measuring the feed composition, and then we will be having an approximate model of the system. From that we will estimate that corresponding to the change in feed, how much will my distillate composition change. On the basis of that approximate, or on the basis of that model, the control value will take the action. So a major difference between both of these control type of control strategies, you can see that here we need to measure the output, and here we need to measure whatever disturbance is occurring in the system. On the basis of that, we will be taking the controller action. So yes, this is a simplified diagram of showing both of this controller. So in feedback controller, we take this controlled output and again feedback it as an input. Whereas in case of feed forward controller, I will measure the disturbance, which will change my output. And on the basis of whatever disturbance that there is, we will be changing the input and correspondingly at the desired output. So this is a extended block diagram for this feedback controller. So a feedback controller block will consist of the following blocks, such as the first one is process output given by this Y. It can be pressure, temperature, flow, level, composition, and we use a suitable measuring device. So over there, we will measure this output, the physical quantity of the output using this measuring device. And then we will be having a set point. So we will be comparing whatever my output is with this set point. And on the basis of that, we will be calculating an error. The controller will take this error as an input and calculate the appropriate control action. So this C is the control action, and this control action will be implemented by this final control element. So usually this is a control valve. So it will either control the flow of the input, the temperature of the system, all these parameters it will control to get us to the desired output. So these are all the different elements of this feedback control system. So if we have to write the equations governing this feedback control loop, we can do it as mentioned in this slide. So first of all, we'll start with the process output. So this process output Y, you can see that it is Y over here. Similarly, in this also it will be Y. Over here, it will be also Y. So this Y is basically summation of this input plus this input. And corresponding to that, we will be having some transfer function. So let's say if I'm having a transfer function of GD over here and process is GP. So we can write this process as Y of S is equal to GPS upon GDS by this equation. Similarly, if we take a look onto this measurement loop, we can write it in this way: ym is equal to transfer function of this measuring element into this output ys. Then this will be fed to this comparator over where we will be calculating the error. So the error will be the difference in the set point and the output that has been measured, that is ysp minus yms. Then we will be having this controller. The controller will give us this control action C. So the control action, we can write it as C of SSGC into error. And then the final control element will take the control action that has to be implemented by the process. So that is, its output will be U will be G control element. If the transfer function of the final control element is GF, so it will be GF into C times. So our main task from this study is to develop a correlation between Y as a function of disturbance and YSP. So what we will do is we'll replace this U in terms of YSP using all of this equation. And if you carry out this activity, you will be getting such an equation corresponding to the output, and it relates to this set point change and disturbance change. So if I have to simplify this first term, I can just simply write it as GSP corresponding to the set point, transfer function corresponding to the set point. The second bracket, we can call it as G load, or the disturbance, transfer function relating the disturbance to the output. So that is, we can simplify this as YS is equal to GSP into YSP plus G, let's call it a G disturbance into disturbance. So this is, we are getting the output equation. So now there can be two type of control objectives. So the first one is when a set point of a process undergoes a change while the disturbance affecting the process remains the constant. So that is disturbance is equal to 0. The objective of the control system would be to steer the output as close as the set point trajectory. So the first one, this kind of study, we call it a servo problem. What do we do in this kind of studies? Let's say if I am having a tank and its set point is YSP. So the set point is the level that needs to be maintained in this tank. Now I provide it the trajectory that initially the set point should be 10. After 1 hour, the set point should be increased to, let's say, 20. So, and I have to change the manipulated input F input such that this trajectory of this set point is followed. So over here, such a kind of problem is known as servo problem. So no matter whatever disturbance in the system, I have to maintain the level of 20 or level of high 20 after 1 hour. So that is set point is undergoing a change and we have to maintain that set point. So the other kind of problem would be, so in this, if we give, let's say, a fixed set point of 10 and the disturbance in the disturbance are occurring in the system due to which this set point can fluctuate. Now my main task will be to reject all those disturbance and maintain this set point to a fixed value of 10. So such a kind of study is known as regulatory problem, also known as disturbance rejection. So we will be rejecting the disturbance or nullifying the disturbance to maintain the set point as constant. So since we are keeping the set point as constant, to find the corresponding transfer functions, we can simply put YSP equal to 0 for disturbance rejection or regulatory problem. Similarly for servo problem, we can straight away put the disturbance variable as 0. Now let's take a look on this feed forward control system. So as mentioned earlier, so in feed forward control system, we won't be measuring the output, but we will be measuring the disturbance of the system. So this is what this block diagram shows. So I am having a disturbance as an input to the system. Then I am measuring the disturbance by using a transfer function of GM, that is the measuring element. Then correspondingly, we will be taking a controller action using this final control element and change the manipulated input to the system by calculating this YSP. So over here, we need to have this accurate process model in order to calculate this, in order to calculate the control action that is to be provided to the process. So that is main difference between feed forward and feedback. Similar to the feedback law, we will be generating the equations for this feed forward. So you can just simply say that in case of regulatory problem, similarly as in case of feedback controller, we will just put the YSP as 0. And similarly in case of servo problem set point tracking, we will put the value of disturbance at 0 to find the controller transfer function. So in each of these feedback controller and feed forward studies, the main task will be to find this controller equation, that is GC. So corresponding to this controller transfer function, we will be finding the parameters of the controller equation. So that is our main task over here. Now just to compare the merits and demerits of feed forward and feedback controller, I have this slide over here. So the first one is the feed forward controller. So the advantages of it includes that it takes coercive action before the process feels the disturbance. So let's say if I'm having a tank and the stone falls over here, then on the basis of this, whatever disturbance I'm providing to the system, it will change the manipulated input. So it will measure this distance and change the manipulated input. So this is good for sluggish system and or slow and system with large dead time, and it doesn't affect the stability of the process. And demerits it requires the measurement of all the disturbances. So the control action that I am taking is by measuring all of these disturbances. So I need to account for all the disturbances that can affect my final output of the system. Similarly, I need a perfect model of this, a near perfect model of the process. And also this, since we are providing a model to estimate the control action, we need to accurately know these process parameters, or else the output will be sensitive to the variation in the process parameters. And for the feedback controllers, it does not require any kind of disturbance measurement. It is insensitive to mild errors in modeling. And it is insensitive to mild changes in process parameters. So basically for feedback controller, we are simply measuring the output. So we don't need an accurate model for taking the control action. However, the corrective action will be only changed if the output changes. So no matter if I'm changing the disturbance, if it doesn't have an effect on my output, so the corrective action won't be taken. And also, let's say if I am at t equal to 0, I'm introducing a disturbance and it affects, it is felt at time t equal to 1 hour. So that is basically the effect of the disturbance is felt after a large time of 1 hour. So when the effect of this disturbance is measured, then only it will take the corrective action. However, what ideally it should have done, as soon as this disturbance occurs, it should take the corrective action. It should not wait for 1 hour. So that is why such a kind of this feedback control are bad for sluggish or systems with large dead time, and this may affect the stability of the process. So these are the advantages of feed forward and feedback controller. So usually in industry, if we in majority of time, a combination of both of these feed forward and feedback controllers are used. So if we looked upon this regulatory and servo problem. Now, in the next class, we can discuss this controller equations in detail and the response of each of these controller. So let's take a look on one example relating to this feed forward or feedback controller loop. So the question is, for a closed loop system, consider the following transfer function. For the process, the transfer function is GPS, controller is GCS, measuring device is GMS, and final control element is G of S, given by each of these equations. The offset in the closed loop response due to a unit step change introduced in the set point of the output variable is dash. So corresponding to this closed loop system, we have to find the offset. So how do we define offset? So let's say if I'm giving a set point of this, let's say YSP to the system, and I am implementing a controller, a closed loop system to reach this set point. So offset is defined as, so let's say after taking the control action, it reaches this ultimate value. So this difference is known as offset. So controller might not reach this set point accurately, and this deviation is, we call it as offset. So let's take a look onto the video solution. Hello everyone. We are solving the off point. So to start, so here we are introducing a change in the set point, and we haven't been given any information about the disturbance. So we will take disturbance as 0. So if YSP is my set point, that will be my input. It will go from here. Then first we will be having the controller transfer function, that is GC. After that will be followed by the final control element, that is gf is equal to 1, and at last we will be having the process transfer function, that is gp is equal to 2 upon 7s plus 1, and then we will be taking the output. Now again we will be having a feedback loop which will measure this output y, and its transfer function is gm is equal to 1, that we will be adding it over here. Now if I have to write the transfer function corresponding to this entire closed loop system, we can write it as ys upon ysp. So this upon this, so we will be going in this direction. So the numerator will be the multiplication of all these blocks gc, gf and gp. It is gc, gf, gp, and the numerator will be the multiplication of all the transfer functions in the feedback loop. That is basically all the transfer function in this loop. That is 1 plus gc, gf, gp and gm. So we can replace the transfer function of this individual element and then simplify it. So let's just replace it. 2 into gf is final control element is 1, then gp is 2 upon 7s plus 1 upon 1 plus 2 into 1 into 2 upon 7s plus 1 into gm is 1. That is, we can write this as 4 upon 7s plus 1 upon 7s plus 1 will go in the numerator, 7s plus 1 plus 4 upon 7s plus 1. That is, we can further simplify this as y of s and ysp of s is equal to, so this 7s plus 1 will get cancelled out and will be 4 upon 7s plus 5. So we have this transfer function of this closed loop, and now we have been given a unit step change is introduced in the set point. And that is, we are having ysp of s as 1 upon s, and corresponding to that we will be having ys as 4 into 7s plus 5 into this ysp, that is 1 upon s. Now in this question we have to find the offset. So we define this offset as whatever the set point is minus the ultimate or the final value or the steady state value of the system, that is y of infinity. So here we are introducing a step change in the set point, so that is ysp will be 1, and we have to find this y infinity. So to find this y infinity, we can use the final value theorem that states limit s tends to 0, that is y of infinity will be given by limit s tends to 0 s into ys. So let's just replace this ys from over here. So we will be getting limit s tends to 0 s into 4 upon s plus 1 into 1 on s. So over here, no, over here we are having this 5, 4s plus 5. So this will get cancelled out, and we will be having limit s tends to 0, 4 upon 7s plus 5. So this will be equal to 4 into 7 into 0 plus 5, that is 4 by 5 is equal to 0.8. That implies our offset for the system will be 1 minus of 0.8, that is 0.2. So the final answer, we can write the offset in the closed loop response due to unit step change introduced in the set point of the output variable will be 0.2. I hope all the questions discussed in today's class were clear. If you have any doubt in any of these questions or the concepts taught today, you can write it in chat box. We will be ending today's session by this example. In the next class, we will be again looking into few more examples related to this feedback and feed-forward control loops. And then we will move on to stability analysis of these closed loop systems. So do you have any doubts, or else we can end today's session? Okay, so thank you for joining. We can end today's session. Hope to see you in next classes too.